Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's get started on our lesson. Third lesson of chapter 1 is called Finding Unknowns. And so in this lesson, we are going to review some of what we have learned in the past about how to solve, how to find unknowns, using some algebraic reasoning, using some reverse thinking. You're going to find that throughout 7th grade, a lot of people are going to solve problems different ways. They're going to have different ways of thinking about algebraic problems and how to go about solving them. And I really want you to explore as many different techniques as you possibly can whenever solving any kind of a problem. I'm never going to be the teacher that's going to say you have to do something one way. The more different ways that you can learn how to do something, the better you're going to understand the math around it and see how these different techniques or these different ways of solving problems are related to each other. Just give you a better grasp, a better feel for how mathematics works. So today we're going to do that doing some reverse thinking. And I'm just going to, when we're working through the problems, I'm going to give you my thought process. Maybe it'll help the algebra make a little bit more sense. So first thing we want to talk about is we are finding unknowns. So what do we mean by an unknown? What is an unknown? So if you take a look at this algebraic equation, x plus 2 is equal to 5, the unknown is the variable, right? It's usually a number. Something plus 3 is equal to 5, right? And I know everyone can figure out what that is without too much trouble. Some of you knew it instantly. Some of you count on your fingers, whatever it takes to get there. I think most of you know that x has to be equal to 3, right? But in its current state, we technically don't quite know yet what that is. So we're putting an unknown there. Now, that unknown, what you may have seen back in first, second, third grade when you were working in algebra and you didn't realize you were doing algebra, was you might have seen something that looked like this. Same exact problem, right? You're trying to fill in that mystery number right there. So what number do you add to 2 to give you 5 for an answer? Well, if you remember your families, 5 minus 2 is equal to 3. That means our unknown quantity would have to be 3. And so when we solve it algebraically, we are not using a box, we're using a letter of the alphabet to represent that unknown quantity. And so we will work through some different strategies to figure out x has to be equal to 3, so we would call this the solution to that given equation. So x in this particular equation is the unknown quantity, which we can figure out by using algebraic reasoning. All right, so what do we have here? Today you will think about how to find a mystery number based on information given to you as part of a game. In the game, you will practice mental math computations and will investigate ways to present different situations. When you solve the number game puzzles, you will also might use a skill called reverse thinking, or reversing your thinking. Reversing is an important way of thinking mathematically. It means solving problems both backward and forward. As you work with your team, ask each other these questions. How can we represent it? What is the best approach for this problem? And have we found all of the answers? Okay, so this is what I'm going to ask you to do. You've got 5 different games here. I would like for you to pause this video and take the time to write these words out, write out these sentences, okay? And then we're going to work through a process, and I want you to see if you can figure out in any way that you like, see if you can figure out what the number is. For instance, for game 1, write down when I triple my number and add 5, comma, I get 11. What is my number? Now, you don't necessarily have to write down what is my number if you want to save yourself a little bit of writing, as long as you write this portion down, which tells you everything you need to know about your algebraic equation, right? So when I triple my number, what does that mean to triple something? You multiply times 3. My number is going to be the unknown quantity because you don't know what the number is yet, right? That's the whole point of this game, is to figure out what is my number. And then you add 5, so it's plus 5. I get is the same thing as writing the equal sign. So 3, I'll just go ahead and show this first one. 3 times your number plus 5 is equal to 11. When I triple my number, there's my number, I'm tripling it. Then I add 5 to it, I get 11. Okay? So what I want you to do is work through every one of these problems to see if you can figure out what the answer is. When you feel ready, you want to see my thought process and how I got to the answers and check to see if your answer is correct, then just come back and we'll see how we did. Okay. All right. I'm assuming you've done some fantastic work. You followed directions, you paused the video, and you went through and you worked through everything. All right. So, what did you get your answer? What did you get for an answer for number 1? Think about it. Let me show you my thought process. I can solve this in a couple of different ways, but one way that I think about is I don't know what the number is, right? But I know this entire quantity right here, when you add 5 to it, you get 11. So what number does this have to be? What do you add to 5 to give you 11 for answer? And you would say 6, right? 6 plus 5 is 11. So I can rewrite this equation as 3x is equal to 6. It has to be. Because if you take 3x and add 5 to it and get 11, then the 3x all by itself had to be equal to 6. Okay? So now I'm going to think about this again, but this time I'm just going to think about the x. 3 times something is equal to 6. So what does that something have to be? 3 times 2 is equal to 6, correct? Which means our solution for this equation, your number needs to be the number 2. Okay, now let's go through and check that to make sure that that works. 3 times 2 is 6, and 6 plus 5 is 11. When I triple my number and add 5, I get 11. That is correct. So x has to be equal to 2. Okay, now let's look at the next one. It says, when I add 2 to my number and then multiply times 5, I get 30. Okay, so this is a little different than the previous one. In this one, you multiplied times 3 first, then you added. Here, it's specifically giving you a sequence of events. It's saying you're adding 2 to your number, and then you multiply times 5. So with the order of operations requiring us to do multiplication first, what can we use to ensure that we will actually add before multiplying? That's where the parentheses comes into play. Remember, with the order of operations, parentheses has the highest priority. The reason why parentheses has the highest priority is because there are some situations like this right here where you actually have to add before multiplying. The only way you can do that is to put parentheses around the addition part of the problem to give that the highest priority. Okay? So this would be the way that we would write this equation. Add x and multiply that sum times 5. Well, until I know what x is equal to, I can't multiply times 5. I know that after I do that, I'm going to get 30 for an answer. So what I want to think about is, all right, what would this quantity have to have been before we multiplied it times 5? If it was this times 5 is 30, then it must have been a 6, right? So that means that the x plus 2 had to be equal to 6. So now we think about this. Something plus 2 is 6. What does that something have to be? And I think you know it by now. It's got to be the number 4. See how this is working? I'm using a little bit of logical reasoning, not trying to get you to solve the problem using a set of steps that you have to memorize. One of the big things about my 7th and 8th grade math classes is I do not want you memorizing processes. I want you understanding why we do what we do. And then you'll learn the process and you won't have to memorize it. It'll just make sense. Okay, so let's take a look at game number 3. See if we can make sense of this. When I take half of a number and add 2, I get 24. All right, so I don't know what my number is, but I'm going to take half of it. Then you're going to add 2. So I wrote this down. Some of you may have said x divided by 2, because when you take half a number, you divide it by 2, right? I decided to write it as 1/2 times x plus 2 is equal to 24. So using our reverse thinking, what would this have to be? This number plus 2 is 24, so doesn't that mean that 1/2 of x has to be equal to 22? Since 22 plus 2 is 24. So I'm going to rewrite this as 1/2 of x is equal to 22. And now, what number do you take half of to get 22 for an answer? And I know many of you are going to make this mistake. It's a very common mistake when you're working quickly and doing mental math. It's one of the reasons why it's so important to show all of your work. The most common wrong answer at this point would be 11. Because you think, oh, half of 22 is 11, right? You just think mentally it's, but it's not. 40. Wait, did I do that? Oh, hold on for a second. You see what I mean? How easy it is to do something mentally and make a mistake, and then if you don't check it, you're wrong, okay? So let's go ahead and check this. Half of 44 is 22. So let's just double check that. Half of my number plus 2 is 24. What's half of 11? That would be like 5.5, right? And is 5.5 plus 2 equal to 24? Absolutely not. I would have, if I had checked that, I would have seen there's no way x could be 11. So now we've rethought it, or at least I have, and half of 44 is 22, and 22 plus 2 is 24. That means that x is equal to 44. So I'm glad I could illustrate for you how even a math teacher that's been teaching for 23 years and is really, really good at math can make a simple mistake by not showing their work. Okay? Very important to show your work. Now let's take a look at game number 4. I'll go back to my yellow. So when I double my number and add 8, I get my number plus 12. Alrighty, now we're starting to get kind of confusing here. 2x plus 8 is equal to x plus 12. A few different approaches that we can take. And I'm not sure that this approach that we have up here, just mentally thinking our way through it, is necessarily going to work here. We could guess and check. What if x was equal to 1? This would be 13, and that would be 2 times 1. That would be 10. Well, x isn't 1. What if x was equal to 2? This would be 2 plus 12 is 14, and this would be 4 plus 8 is 12. Well, we're getting closer. What if x was equal to 3? This would be 15, and that would be 14. That's not it. What if x is equal to 4? That's going to be the winning one. So 4 plus 12 is 16, and 8 plus 8 is 16. So I feel good about x being equal to 4. What I would like to do is I would like to show you, oh, why did I do that? No, 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 no. Yes, yes. X equals 4. Okay, let's bring this over to the side. Let's show another way that we could work through this. We are going to learn, I'm not quite sure how much you did with Mr. Harbour last year, but we're going to learn about this legal moves for solving equations in algebra, where whatever you do to one side of the equation, do the exact same thing to the other. Now, I don't like the fact that I've got x's on both sides of the equation. Luckily, I can take away an x from each side. So if I take away this x, it's no longer there, right? It goes away, just leaving me with the 12. And if I take away one of those x's, do you see how I've got 2 of them? 2 x's. Well, if I take away one of those x's, that means I've only got 1 x left, plus I still have the 8 there. Okay, that's called the removal of balanced sets. Now, I'm back to where I was up here. Something plus 8 is equal to 12. What would you add to 8 to give you 12 for an answer? Well, sure enough, it's the 4. So we feel good that 4 is our answer. So let's check it just to make sure. When I double my number, when I double the number 4, I get 8. And I add 8. That's going to be 8 plus 8 is going to give me my number plus 12. 16 is equal to 16. Yes, that is correct. I feel good about my answer. Okay. And now for the last one. When I double my number, am I going to highlight this too? Yes. Let's go back to the highlighter. Highlight. There we go. When I double my number, add 4, then subtract my number and add 3. Holy moly! Then I get my number plus 1. There's a lot going on there. All right. What's the equation that we have for that? All right. So when I double my number, then add 4, then subtract my number, then I subtract 3. I get my number plus 1. Okay, so here we're going to talk about combining like terms. Now, I don't know how much you did with the algebra tiles in 6th grade. We're going to spend a fair amount of time with algebra tiles in both 7th and 8th grade for you to fully comprehend, for you to fully understand why we do what we do. But basically, what we can do here is combine like terms. Combine like terms. Here we go. So you got 2x's and a negative x. It's kind of like saying 2x's minus 1x is going to be 1x, correct? And then you had 4 and a negative 3, so that's plus your 4, and your negative 3 becomes plus your 1 is going to be equal to x plus 1. Oh, isn't that interesting? Are they equal to each other? Yes, they are, right? This quantity is the exact same as this quantity, but what do you notice? Whatever number I plug in here, I'm going to plug in that number here, correct? So doesn't that mean that x can be any number? Will every single number work here? I don't know. Let's check this. First of all, I'm going to start with the number 0. If I take 0 plus 4, that's 4, minus 0, that's still 4, minus 3 is going to give me 1 for an answer. Is 0 plus 1 equal to 1? Yes, it is. What if x was equal to 5? This would be 2 times 5 is 10, plus 4 is 14, minus 5 is 9, and 9 minus 3 is 6. Is 5 plus 1 equal to 6? Yes. So x can be any number. That was a tricky question. Another way of saying that is there are infinite solutions that would work for this given game. Any number that you would have picked would have worked in here. Because by the time we simplify these two equations or these two expressions, they end up being the exact same expressions. So, this process that we're working through right here is what we refer to as algebraic reasoning, algebraic thinking, yes, algebraic thinking, and however you choose to attack a problem, whether you choose to use some logic, reverse thinking, or do what I did here and actually show the steps along the way, which we'll practice quite a bit this year. All of them work. The more complicated things get, the more you need to rely on working through the processes, which is why we're going to practice this so much. If all of our problems are relatively simple, like 1 or 2 step equations, a lot of people can solve those in their heads. But we are going to get to like game 4 and game 5 where things get a lot more complex. So we'll want to practice how we show our work and how we check our answers. Okay, so I want to talk to you a little bit about the nature. You like my picture there? I've worked really hard on that. The nature of what algebra is. Okay, so when we were little, we learned how to do 5 plus 2, and then we would just answer those questions, correct? So our unknown quantity, which we are writing in place of our box, is the answer. That's the thing that we're trying to figure out, right? In algebra, however, we often know what the final answer is. And what we're trying to figure out is, what did you have to begin with? Okay? So I like to use this as an example. When I was growing up, when I was in 3rd, 4th, and 5th grade, I used to live out in the country. And our house was a short walking distance to a pond where I would like to go and skip rocks. And so on a nice summer day, I would walk out, I would go and start walking down a path that through our fence at the border of our property, and I'd go out into a field and I'd walk past a pile of rocks. And I'd look around for the really good skipping stones, right? And then I would continue on through a little forested wood area, and I would get to a pond where someone was nice enough to have created a nice little kind of a pier that went out into the water a little bit. We'd go swimming in this pond too, but you can go and skip rocks really nicely. And so think about it this way. I am on my way out, and I've got a bag of rocks, okay? I don't know how many rocks are in that bag, so I'm just going to say it's an unknown, right? And as I'm walking, and I look and I say, hey, there's some really good skipping stones in here. I think I'm going to double the number of rocks that I have in my bag. So I pick up some skipping stones and put them in the bag until I've doubled my stash. So now, if we started off with 5 of them, now I have 10. If I started off with 7, now I have 14. Okay, but I don't know how much I started off with. Not yet. I mean, I kind of do, but you don't. If I were doing this for you. So then we continue along the way, and sure enough, there are a few rocks that you pick up along the way. And so I find 2 more rocks, and so now I have 2x plus 2, and then I dump all the rocks out, and there are a total of 18 rocks that are there. So now, can you tell me how many rocks I started with? The process for getting back to where you started is the exact reverse order of the order of operations, right? We started by doubling, then we added 2, and at the end we got 18. So if I were to go back in reverse, like play this in a video in reverse, the last thing I did was I added the 2 rocks from this little forested area. So if I undo that, I would have to take away 2 of the 18 rocks that I had, which would mean that I would have a total of 16 before I had walked through the woodlands. And here, when I was at the rock pile, I had doubled my stash. So if I undo, what's the opposite of doubling something? Divide it by 2, correct? So if I divide each that by 2, then I'm dividing my 16 by 2, which means I must have started with 8 rocks when I left the house. So just so that you understand this, PEMDAS is the order of operations for when you're working with numerical expressions. First you do parentheses, then exponents, then multiplication and division, with the last priority given to addition and subtraction. But when you're solving algebraic equations where you know the answer, you just, like here's our answer is 18, right? You just don't know what you started with, you're going to actually go in reverse order as we solve these problems algebraically. So I will bring this kind of a model throughout the year, the idea of working your way backwards. Now, you don't necessarily have to work through it backwards. This is like the algebraic process. We could have done the exact same thing where we said, well, that must be 16, right? And 16 plus 2 is 18. And then this x must be 8 since 2 times 8 is equal to 16, so x has to be equal to 8. You can do it that way as well. But when things get complicated, this reverse thinking, this going in the reverse order of PEMDAS to solve algebraically becomes essential. Okay, so that's it for today's lesson. How much time did I use? 22 minutes, not too bad. That's below 25, but I think maybe tomorrow, maybe I can get that under, or for our next lesson, whenever that is, hopefully I'll be able to get that under 20 minutes because I don't want you to have to spend too much time on it. All right, take care. Good luck on your homework.
Hey, feeling good, like I should. When in dark, walk